Welcome to a somewhat comprehensive guide to gene regulation by Chase McCoy. I'd like to shout out my genetics group, the Mitochondrias. You guys are great. Okay, so as we move into gene regulation, we're going to be today talking specifically about the lac operon. Now, as you can see, it's a negative inducible operon that controls the transcription of genes needed for the metabolism of lactose. Now, as we continue through this entire lecture, commentary, whatever, we need to keep this in mind of the actual purpose of the lac operon. Now, moving on, we're going to talk about the basic structure of an operon, and it's as follows right here. So we have our regulator gene up front, followed by our promoter, then our operator, and our structural genes. These are very, very important with the metabolism of lactose, but we'll get to that. So written out, we see lac I, lac P, lac O, lac Z, Y, and A. And these are color coordinated, so you can see each corresponds with the same color. Alright, what we're going to do first is just discuss the functions of these genes. Now, starting with our structural genes, we have lac Z, Y, and A. Now, respectively, you see lac Z encodes B-galactosidase, and unwritten, but we know that B-galactosidase allows for the cleavage of lactose, which is a very important part in the metabolism of lactose. Lac Y is going to encode permease, which allows for the absorption of the lactose. And lac A encodes transacetylase, and I have no idea what that does, but it's important. Moving on, we have our operator genes, which is written out as lac O, which allows the regulatory protein to bind to it. And now, don't worry, we'll get to the regulatory protein and how it plays a part in this whole process. And our promoter genes, written as lac P, bind with RNA polymerase, and that is going to induce the transcription. Granted, this is a whole chain of command here, so we'll see how they all work out, but this is the function of specifically lac P and lac O. And finally, lac I is our regulator gene, and that's going to produce our regulatory protein, what we talked about with our operator gene. Okay, so discussing our regulatory proteins. These can either be repressors or activators. Now, this is where we start to get into the types of control that we can have over our operons. So, we have two types of operons, which are inducible and repressible. Inducible, inherently, the transcription is off, versus repressible, the transcription is on. Now, comparing this and working in tandem with the transcriptional control, we have negative control and positive control. Now, this can get very confusing, and we're going to work on it very shortly after this. But briefly, negative control, the regulatory protein, which is created by lac I, remember, is a repressor, which is going to inhibit transcription. In positive control, the regulatory protein, created by lac I, is an activator, which is going to stimulate transcription. Now we're going to keep these in mind as we move forward and work on some examples. Okay, so here are some examples or possible ways of control. We have positive inducible, positive repressible, negative repressible, and negative inducible. Now, these are going to be the regulatory proteins that are created by these types of control. So, with positive inducible, now we know it's inducible, so it's going to be inactive. Remember, right up here, transcription's off. So it's inactive, and it's going to be an activator because positive control, right? It's just matching at this point. So we know that it's going to need substrate to activate transcription. Same thing with a positive repressible is going to be an active activator, which is going to need substrate to repress transcription. Now, some people can get confused and turned around between the positive and negative and the inducible and repressible. But if you come back to what the function of the operon that you're focusing on is, it's all pretty straightforward. You can normally figure it out. Now we have our negative repressible, which means it's going to be an inactive repressor. It's going to need substrate to activate the repressor. Make sense? And then this negative inducible, that should sound familiar because that is what our lac operon is going to have an active repressor as a regulatory protein. It's going to need substrate to deactivate the repressor. Inherently, transcription is going to be off, right? So, knowing that it's going to be off, we're going to need that substrate to deactivate it in order to transcribe. Okay, so now we're going to see how good I am at doing two things at once. But we're going to see how the lac operon works just inherently with and without lactose. So here, no lactose is present. We know that our operon is a negative inducible operon. So that's going to create, oh boy, an active from lac I. It's going to be creating an active repressor. So that's going to come around this operator gene, and it's going to repress it. Now, we're going to have a little slot right here where if lactose was present, it could deactivate the repressor, but there is no lactose, so that cannot happen. That means there's going to be no transcription occurring, nothing will happen, because no lactose is present. Now, here we are down here. Oh my goodness, look at this beautiful lactose. How delicious. So, we have lac I creating this active repressor. We have this bonding site, right? Binding. The site where the lactose can bind. So, this lactose is going to come right over here, bind to this repressor, and that is going to allow the operator to do its job. Now, the repressor has been deactivated and transcription can occur. Okay, so this has been an example of what happens with and without the presence of lactose. Now, this is with all the genes operating as they should and nothing's going wrong, nothing's inactive, and so on. But we need to learn about that now, don't we? Yes, we do. Okay, so here we have some mutations and statuses of the genes. Now, with our structural genes, we have basically plus and minus, which is how it'll be written, which basically means active versus inactive. Now, we see LAC-C plus, basically, it's going to encode because it's an active structural gene, as opposed to LAC-C minus, which is an inactive gene. It's not going to encode anything. Now, moving on to our operator genes. We have LAC-O minus, which is going to be an inactive operator. LAC-O plus, which is going to be an active operator. And then we have our first mutation, which is going to be LAC-O-C, which is a constitutive mutation. It's going to prevent the binding of LAC-I repressors, and it's going to have transcription always on. Now, this is still cis-acting, and don't worry, we'll get to what that means in a second. But basically, this LAC-O-C mutation, always going to be operating, always going to be transcribing, no matter what the LAC-I gene is doing. Now, we have our promoter genes, which basically is going to be positive and negative, active and inactive. Now, our P minus is our mutation for this. It's going to be inactive promoter. It's going to prevent the binding of RNA polymerase. This also is still going to be cis-acting, and don't worry, we'll get to that in a second. But if RNA polymerase cannot bind, transcription cannot occur. Now moving on, we have our regulator genes, which is LAC-I, minus, plus, and LAC-I-S. Now, LAC-I minus is going to just produce mutant repressors. They're not going to work. LAC-I plus is going to be an active regulator. It's going to work fine. Now here we have our super repressor mutation. Now this LAC-I regulator gene with this mutation is going to create a regulator protein that cannot bind to a substrate. No transcription will occur at all. And now, something to keep in mind is this is trans-acting, and we'll get to that in just a second. Now, what can be confusing for some of you is how these operons are written out and how we're supposed to be expected to really understand what's going on. Now, it's going to basically be cleaved in two by this slash. So, we're going to see this first half is going to correlate with this top half. Same with this second half with this bottom half. So these are going to be the parts of the operons that we're seeing. Now remember, as we were discussing the mutations about LAC-I, P, and O, and how LAC-P and LAC-O are both cis-acting, whereas LAC-I is trans-acting. Now that is going to be in reference to whether or not these can influence other sides of or influence parts of the gene that they're not touching. So we know that LAC-I is transacting. So because this is an active inhibitor, right? It's transacting. Even though this is inactive, it's still going to be able to inhibit this side of the gene. LAC-I can affect LAC-O on its own side, the one it's touching, but it also can act in a trans way. Whereas LAC-P and LAC-O will only be able to affect the genes that they're in contact with. So we see an inactive promoter right here, but just because this is inactive does not mean that the promotion will not occur with this side of the gene. We have an active promoter here, so it's going to work. All right, so now that we really understand how operons work and how all the mutations affect each other, we have an example problem. We have a partial diploid with this genotype. Now the question is, will this genotype be able to produce B-galactosidase? Why or why not? Now we're going to walk through it. If you want to pause really quickly and answer it yourself, go right ahead, but here we go. All right. So right off the bat, we're going to notice that our LAC-I gene has a mutation. Now this is going to be a super repressor. It's not going to allow any substrate to bind to it. It's going to stop all transcription occurring. But we need to keep in mind that this repressor needs to bind to the LAC-O gene. Now considering the LAC-O gene also has a mutation, this super repressor, all angry and mean, yeah, I'm giving him emotions. He can't even bond to this. It's not going to happen because the constitutive mutation prevents the binding of the repressor. So transcription is going to occur. Now we notice on this side right here, both with our operator, promoter, and regulator genes, there are no mutations. So everything is going to flow smoothly. But we have one big problem. In both of our structural genes, they're inactive. So even though we overcame our super repressors and we managed to have transcription occurring, the inactive LAC-Z gene means that no B-galactosidase is going to be occurring anyways. So unfortunately, it's not happening.